Ngalakin Khadijan Nyunga Boja.
Now let's move on to the next page. So in this slide, we can see a very special case of the joint distribution. In this case, there are two random variables, x and y, and both are following the Gaussian distribution, or in other words, following the normal distribution. Okay, and in such case, the jointly distributed random variables have some special features. In this case, let's focus on two things. One is the joint PDF, the other one is the marginal PDF. In this page on top, you can see the first formula, which is really long one. So this fxy is the jointly Gaussian distributed random variable PDF. And in this formula, in the middle part, you can see we have the exponential function. And we have using this exponential function to divide by something. So these features remain same as what we have introduced to the Gaussianly distributed single random variable case. But because you have two random variables, the whole thing becomes more complicated. And in this case, I didn't expect you to memorize this formula. If we have such questions in the test or exam, so this formula will be given. But you must understand the notations used in this formula. For example, rho xy, or that is a correlation coefficient between the x and the y, of course. Mu x, mu y, and mu y, they are the mean values of the x or y, respectively. The sigma x squared, sigma y squared, okay, they are the variance of these two random variables. By the end, this is sigma x and sigma y. They are the standard deviation of these two random variables. Okay, you need to understand how to derive these different parameters for this calculation. Formula itself will be given in the formula sheet in the test and exam. Okay, so this is about the joint PDF for Gaussian distributed random variables x and y. And in addition to this formula, the property is important. This property is dedicated for the Gaussianly distributed random variables. If the x and y are Gaussian distributed random variable, so we can say the marginal PDF. Okay, we have introduced to how to calculate the marginal PDF, right? So we are using this formula and put this joint PDF into that integration to finish calculation. This will involve a long calculation, so I skip that. I just give you the final decision, final result. So the marginal PDF of x or the marginal PDF of y is also a Gaussian distributed random variable PDF. So the format of this result are exactly the same as to what we discussed regarding the single random variable Gaussian distributed random variable case. So in other words, this property is saying if x and y are jointly Gaussian distributed random variables, so the marginal PDF for each of the two random variables are also Gaussian distributed. Okay, very useful property which we are going to use in maybe chapter 2 or chapter 4. Okay, and another important property is, okay, again the condition remains same. The x and the y are jointly Gaussian distributed. If x and y are uncorrelated, again, don't forget what is the uncorrelated. Uncorrelated means x and y do not have linear relationship between each other. If this is the case, then we can say the x and y are also independent. That means if the x and y are Gaussian distributed random variables, if they do not have linear relationship then they don't have any relationship. That. Okay, easy concepts, easy properties, but very useful. Please make sure you understand that. Okay, the mathematical induction behind the formulas, to say the truth, are not very hard. If you have interest, you can try them out, but they are not required in this unit. Okay. Now let's move to the second topic of this lecture, the vector random variables. Actually, before this slide, in the first section, what we have already discussed are just the cases with two random variables, x and y. Now we want to move one step further. So if there are more than two random variables, how can we handle that? So what are the properties of them? So in other words, you will be given a group of random variables, and generally we organize this group of random variables into a vector. So it's why we say this is a vector of random variables. Now let's have a look at the details of this topic. First of all, notations. Now let's have a look at the first definition. Okay, the total number of this group of random variables is n, lower n, and each random variable within this group is denoted by the x1 or x2 until the xn. So you can see the notations are given here. So we have x1, x2 until xn random variables. And as we mentioned, this group of random variables will be organized in one single vector. So normally we put them into a column vector. And we give this column of vector a name. The name is the capital X. But this X normally will be used another font. We call that boldface font. If you see the boldface font, that means we got a vector or matrix, of course. With instance x equal to so another vector, so lower x1, lower x2 until lower xn, and this group of x parameters will be organized into another vector which is called lower x, boldface font, a vector. Okay, so we call that as the capital X vector and the lower x vector for these two cases. And for the integration part, by the end of the integration, you have dx or dy stuff, right? But because for this question, we have a group of random variables. So you have the dx1, dx2, and dxn. So we are using the boldface font lower x to denote the sequence of dx1, dx2, dx3, and so on. Okay, this is just the notations we used. And next one, multiple variance joint distributions and probabilities. Actually, all the terms are now new to us. We just need to use the new notations to understand them. Okay, first one, joint CDF. Capital F for CDF, no problem. And the subscript is again the vector X. That means we got a group of the random variables in the vector. Okay, and inside of the round brackets, you got the vector lower x. That means a group of parameters, one for each of the random variables. And that is equal to, I think this thing is very general form for this group of the random variables. And this joint CDF, no surprise, is defined as the joint probability that the first random variable x1 is smaller or equal to the corresponding lower x1 value. And in the meantime, so because this is joint probability, right? So in the meantime, the second random variable is smaller or equal to the second given parameter x2 again and again until the very last xn random variable. Okay, so again, this is the same idea. So joint probabilities, and each random variable value is smaller or equal to the given parameter. That. Okay, joint PMF. Join the PMF. That should be a simple one because when we call PMF, so we are talking about the discrete random variable cases. And for this one, the joint PMF is actually indicating the probability for this group of vector of random variable x that the random variable values are equal to the corresponding given parameters. So this is another joint probabilities. Okay. Next one, joint PDF. Actually, joint PDF comes from the joint CDF. Okay. Sorry, I should use the thinner pen. Comes from here. So we have defined the joint CDF here. The joint PDF is n times or n order partial derivative of the corresponding CDF. So actually in the two random variables cases, we have already learned this one. In such case, n equal to 2. So in this case, now the n is increased to a number higher than 2. But you just repeat the same procedure as n times, not only 2. Okay. And finally, n-dimensional event probabilities. In this case, okay, we want to evaluate what is the probability that the x vector is falling into A. So actually, in just 2 or 3 slides before, we just finished the discussion of this one. So very similar thing. So we just need to do the n times of the integration. And inside of integration, we just need to put this joint PDF. And then guarantee all the x parameter values are within the A region. Just that. Okay, not new at all. Okay, this is just all the notations used in this case. Let's move on to some extensions. So marginal and conditional PDFs. Okay, again, not new. You have learned that in the last discussion. Okay. Now here in our hands we have in total n random variables. But if you want to evaluate the marginal PDF of one single random variable out of these n variables, for example, I want to evaluate what is the marginal PDF of x1 random variable only. So this means we want to eliminate the effect of x2, x3, x4 until xn. So we have to, using that formula we learned from the two random variables cases. So we repeat the integrations n-1 times. This n-1 times integration are conducted regarding the x2, x3, x4 until xn. By doing this operation, so we are eliminating the effect of the x2, x3, x4 until xn from this joint PDF. After we finish the evaluation, the remaining thing is the marginal PDF of the x1 only. Then finish. Again, for two random variables cases, the n is equal to 2, and we have done the discussion. If you can't understand this part, please go back to the two random variable cases and record that part. Okay, and this is one case. So okay, another case is we want to evaluate the marginal PDF of x1, x2, x3 until xn minus 1. So that means this PDF or this joint PDF are with respect to the first n minus 1 elements or random variables. So we can say we want to eliminate the xn from this evaluation. In such case, we just need to do the integration to the joint PDF with respect to the xn. After this process, so this xn effect is eliminated, and the remaining thing is the marginal PDF for x1, x2 until xn minus 1. So actually, these two can be treated to be two examples. For example, if I want you to evaluate the marginal PDF of x1 and x2 only. So what you need to do is just to conduct the n minus 1 integration with respect to x3, x4, x5 until xn. The same procedures. Okay. Okay, this part is easy. Next part, the conditional PDFs. in this case, on the left-hand side of equation, you can see we want to evaluate the PDF of the xn only. So you can see here, so I'm showing you. This xn is indicating I have the interest in this xn only, subject to the condition that we know the values of x1, x2 until xn minus 1. So except xn, I know the observations, I know the conditions. Based on this condition, I want to know what is the PDF of the xn. So by using, again, the Bayes theorem, we are able to derive this relationship. On the top of the fraction, on the right-hand side, is the original joint PDF for all n random variables. At the bottom, it should be the marginal PDF of conditions. But in this case, our conditions are from x1 up to xn minus 1. So at the bottom of the right-hand side fraction, this part is the marginal PDF of this from 1 to n minus 1. So in total, n minus 1 random variables. Okay, easy. And by the end, the very last so-called property is about how to calculate the joint PDF for n random variables in this vector by using a conditional PDF. Okay, so I think this step is just recursive steps based on the previous formula. So you can use this formula to derive the next one. So what we are doing is just to multiply the bottom of the fraction to the left-hand side, and then repeat this procedure for different xn minus 1 until x1. So this is in here. So it's why I say this is recursively processing. Okay, very simple. I leave that to you. Please make sure you understand these properties. Okay. Independency. The collection of random variables x1 up to xn are independent between each other if the joint PDF equal to the product of the individual PDFs of these random variables. You can see this joint PDF equal to the PDF of the xn multiple the PDF of xn minus 1 again and again for all the random variables. If this is true, you can say, okay, all the vectors, all the random variables within this vector are independent with each other. And this also indicates such relationship. So the PDF of the xn random variable subject to the condition of x1 to x2 to xn minus 1 is equal to xn, so the PDF of the xn. This is because of the independency between the random variables. This means if the x1, x2 until xn minus 1 do not have any relationship with xn, so knowing or not knowing the condition will not affect the PDF of xn. Okay, so again, we have discussed this one for two random variables cases. If you forgot this, please reverse back and go back to check the discussions. Okay, next one, expectation. So we're just repeating what we have learned before. Okay, so for this vector of random variables, the expectation of the g function, which is a function of this vector, is equal to the n times integration. And inside of integration, we are using whatever you have here, multiple the joint PDF. The result will give you the expectation of the g function. This is for continuous case. For the discrete case, roughly the same thing. We just need to replace the integration of the continuous cases to the summations and replace the fx dx to this joint PMF. So this is just a pair. So one for continuous, one for discrete. Okay. Sums and the products. Okay. Expectation of the summation A by G, because inside of the expectation operator, we got a summation of a sequence of terms. So we can put the expectation operator to each of the G of I function. We mentioned the expectation operation can play some effect to the random thing only. So AI is not necessary to stay inside of the expectation operation. Okay, this is pretty simple. But when you use this thing for the expectation of the product, you must be careful. You can do so. You can move the expectation operator around the GI function, no problem. But condition is all the random variables must be independent. So please be very careful with this condition. If they are not independent between each other, so this rule will not be valid. Okay, so be very careful with this one. Some students make mistakes on this. Okay. Okay, now let's move on to the hard part for the vector of random variables. Now we are going to discuss about some matrix calculation of this topic. First one is simple. So how to determine mean for a vector of random variables? So we are using, again, you can see here, a boldface font mu to denote this is a vector or matrix, of course. Mu x is a vector. This vector is the expression of the vector x. Now, for the vector x, we can just put the vector of the random variable here. So we are doing the expectation operation to this vector. So this expectation operation can be given to each element in this vector. So you can say we are deriving this in here. So in other words, if I want you to evaluate the mean vector for the x vector, you just need to calculate the mean for each element separately. And then the result will be in the same dimension vector. That will give you the mean vector for this x vector. Okay, so mean vector is simple one. Correlation matrix. Okay, important and a bit hard, and a bit harder in the chapter 2. Okay. First of all, this matrix is called correlation matrix, denoted by the, again, boldface font R. This indicates this is a matrix. Okay, and this matrix R must have dimension n by n, so n rows and n columns. This n is the number of the element in the vector x. Okay, and we calculate this correlation matrix by using the equation to the x-axis vector of random variable. That is a column vector, right? X by x transpose. This small t on the superscript is indicating the transpose operation. Okay, x is one n row, one column vector, and after transpose it, the x transpose will have one row, n columns. So using this one by this one, so x by x transpose, the result will be n by n matrix. And then you are going to carry out this expectation operation to each element within this square n by n matrix. That's the result gives us the n by n correlation matrix. And each single element within this matrix is R11 or R12 or Rij. For example, we say this is Rij. So what is Rij? Rij is actually expectation of the xi, xj. Xi is the ith element in the x vector. Xj is the jth element in the vector. Xi by xj is the product of these two random variables. And then the Rij element is the expectation of this product between the two random variables. Okay, this is about correlation matrix. It seems to be pretty easy, right? But this part is actually very hard. So we are going to use it in our future questions. So let's just move on. We are going to review that version. Okay. A small example. Oops, sorry for that. A small example. Now we have one very simple vector which consists of 3 random variables. Sorry guys, there's a typo. So this should be a column vector. So I forgot transpose T to this row vector. So actually this X vector is equal to X1, X2, X3. So I mean this, okay? This will be a vector of, be very careful with the following 4 conditions. Independent, zero mean, unit variance, Gaussian random variables. Okay, these 4 conditions are very important. So first of all, independent. This is good condition, right? So if you can say one vector is independent, that means all the random variables within this vector are independent between each other. That means between x1 and x2, no relationship. Between x2 to x3, no relationship. Between x1 and x3, also no relationship. Okay, so that. Zero mean is indicating. So for each of these 3 random variables within the vector x, the mean value is 0. So this is indicating mu x1 equals mu x2 equals mu x3 is equal to 0 mean, which gives us the mean value to be 0. Okay, unit variance means the variance for these 3 random variables are all unit, are all 1. It means sigma x1 square equals sigma x2 square equals sigma x3 square equals 1. Finally, the type of these 3 random variables are same. They are all following the Gaussian distribution. So that the question is asking us to calculate the correlation matrix R. So by using the definition we introduced in the previous slide, so we know the Rx matrix should be a 3 by 3 matrix. And the elements around the rows and columns are just Rij. The Rij is defined to be the equation of the xi and by xj, this product. Okay. Now we want you to notice. So actually, out of these 9 elements, they can be divided into 2 groups. The first group are the elements along the diagonal directions R11, R22, R33. And the other group of elements are the elements of the diagonal directions. Okay, so we have different ways to calculate the values for these elements in these 2 groups. So let's have a look. If the I is not equal to j in this notation, if I is not equal to j, that means the element is of the diagonal direction. In other words, they are corresponding to the elements highlighted in blue in this example, right? So in other words, the Rij, note please, I is not equal to j, is equal to expectation of xi by the xj. Now we need to use the condition given question. So all the random variables given in this example are independent. So you can just go back to the previous slides to find the property of the independency. If the 2 random variables are independent between each other, so the equation of the product of the 2 random variables is equal to the product of the 2 separate expectations of these 2 random variables. Like this. And each of the 2 terms is one mean value of the corresponding random variable xi and xj. Now we use the second condition. So for this particular example, for all the random variables in the vector, the mean value is 0. So this is equal to 0 by 0, which equals 0. So that means all the elements of the diagonal direction are zeros. So at the bottom, you can see in the final result, they are all zeros. Okay. Now this is the first group of elements. The other group of elements are the diagonal elements, where the I is equal to j. In other words, the Rij, I equal to j, give us Rii, because j is equal to I, right? So Rij is changed to Rii. Rii is actually the calculation of the expectation that xi by xi itself. Everyone, please be reminded, you are not allowed to write this in to be the exi by exi. This is totally wrong. The reason is, if you want to just finish the conversion from this step to the next step, the important condition is between the two random variables. So xi, xi, or the xi, xj, they must be independent. See here, independent. Then you have this property. You can just put the expectation to each of the two random variables. But you may just consider, regarding the xi and itself, are they independent? No, not really. Actually, xi is highly related to itself. The relationship is very strong, not independent. It's highly dependent. It's fully dependent. In such case, we don't have this property at all. So how to solve the question? Now we use the other way. This is equal to E xi squared. Now we have to use knowledge regarding variance of the xi to solve it. So when we discuss the variance calculation, in other words, the second central moment, okay? So regarding the variance of the random variable xi, that's equal to is that equation of x minus mu xi, yeah, and square of that. So second central moment, right? And this is also equal to the expression of the xi square minus the square of the exi. Or in other words, you can use mu xi here, the same thing, right? So this gives you the mu xi here. Now our interest in this question is to determine this one. So this exi square is equal to the variance of the random variable plus the square of the mean of it. So these two things are the same, right? So this is equal to, for this particular example, the variance are all unit, so which are ones for all the random variables. And the means are zeros. So this is equal to 1 plus 0 square, which gave you 1. So by this calculation, we know the elements along the diagonal direction are all ones in this example. Then we solved this question. Okay, it's done. So very simple example, but I want you to temporarily memorize this result, because when we discuss the next topic, this result will be reused. Okay, let's move on. Next part, covariance matrix C. Let's record conditions we have, right? So we still have the vector of random variables x1, x2 until xn within the vector x. Okay, so this is the condition. Now we want to evaluate next the covariance matrix. We are using the boldface font C to denote this matrix, and this matrix is defined as n by n matrix, square matrix, n rows and n columns. And we are calculating this matrix by using this formula. Again, expectation operation at the outside, and inside of this operation, we are using the x minus the mu x. So that means using the vector x minus the mean vector. And then this is the first term, multiple the transpose of the same vector. X is n by 1 vector. Mu x is n by 1. So n by 1 minus n by 1. So this part is also n by 1 matrix. And the transpose of this vector is 1 by n. N by 1 by 1 by n is n by n matrix. So it's why we have the n by n covariance matrix. Okay, this is how we calculate this in here. But this calculation can be easily connected to the correlation matrix Rx. Okay, very simple mathematical step from here to here. So I am not going to go through that. Very simple. Okay, I leave that to you. So what we are going to do is to expand the A by B term and convert that to 4 terms. So x by x transpose, something like that, and do the explanation one by one. After you finish simplification, you will be able to derive this one. That is so simple. I leave that to you. Okay. So in other words, the covariance matrix C is equal to, you need to memorize this one. Very important. Okay. Is equal to the corresponding correlation matrix R minus the mean vector by the transpose of the mean vector. Cx, the correlation matrix is n by n. The dimension is n by n. For the Rx, n by n as well. And for the mu x, we mentioned is n by 1. And the transpose it is 1 by n. So regarding the mu x by mu x transpose is still n by n. So the dimension are compatible between the both sides of the equation. So everything is fine. Okay, so this is how we derive the formula calculating the covariance matrix. But inside the covariance matrix, the element, so let's use another maybe right pen here, for example. So Cij, what is Cij? Cij is actually very bad. Here, sorry guys, I'm looking for that. Cij is given here. Cij is actually the covariance. So I'm going to write that for you anyway. This actually Cij element within this covariance matrix is actually the covariance between the xi and xj. This is calculated to be the expectation of xi minus mu xi by xj minus mu xj, this stuff. And again, this can be converted to Rij minus mu I by mu j, this stuff. Again, it's easy mathematical stuff. You can do that by yourself, but this just gives you the meaning. So inside of the covariance matrix, each element is actually the covariance between two random variables within this vector. Got that? But you need to be very careful with the elements along the diagonal direction. Because if the element is sitting in the diagonal direction, the second element will be same as the first element. So in other words, so I'm changing now, okay? So this xj will be same as the first variable xi. So if this, okay, anyway, I rewrite for you, okay? If this element is on the diagonal direction, so we have Cii, which is covariance of xi and xi here is equal to expectation of xi minus mu xi by xi minus mu xi. But this term and this term are equal for this case. So that's equal to expectation of xi minus mu xi, then square. This is actually the variance of xi. In other words, in the covariance matrix, all the elements along the diagonal direction are the variance of the corresponding random variable in the vector. And the elements of the diagonal direction are the covariance between the two corresponding random variables from the vector. Okay, there's one more thing we need to notice. So we need a bigger space to write, right? So see here, you see we got one covariance matrix that's equal to, let's just make one simple example, right? C11, C22, C33. This means we have only 3 random variables in the vector x. And this is C12, C21, my fault. What a stupid mistake. That should be C12, C13, C21, C23, C31, C32, C33. Okay, just like that. So we have said along the diagonal direction, these 3 elements are actually the variance of the corresponding x1, x2, x3. So that's the easy part. And off diagonal direction, let's focus on this one and this one. What is C12? C12 element, so this one is actually expectation of x1 minus mu x1 multiple x2 minus mu x2 by definition, right? What is C21? C21 is the expectation of x2 minus mu x2 by x1 minus mu x1. Okay, can you say this term and this term are the same? This term and this term are the same. And between the 2 terms of each of these 2 formulas, we are actually calculating the product. So the order of these 2 terms are not important at all. You can just interchange the position of these 2 terms. So in other words, these 2 things are equal between each other. So that means the C12 element and C21 element are the same. And the similar situation can be found between C13 and C31, C23 and C32. In other words, within a covariance matrix, all the elements must be symmetric about the diagonal direction. Okay, so this is another important property regarding the covariance matrix. Well, I forgot to mention, regarding the correlation matrix, this property remains to be true because R12 and R21 have the same meanings, right? So we go back, sorry to say I forgot to mention it. So regarding the elements within the correlation matrix, we said the Rij equal to the expression of xi by xj. But in the meantime, the Rji, another element, equal to exj by the xi. But these 2 things are equal. This Rij is in the ith row and jth column, and this Rji is in the jth row and ith column. These 2 elements are symmetric about diagonal direction, and they have the same values. So that means in the correlation matrix and also covariance matrix, they are all symmetric about the diagonal direction. Okay. Okay, this part is done. Let's move on to next example. Okay, this example remains the same. So all the conditions are the same as the previous example. The only difference is we want you to evaluate the covariance matrix Cx. Again, I forgot the transpose of this vector, but now you know the x vector is equal to a column vector x1, x2, and x3. And how to calculate the covariance matrix? So because the dimension of the x vector is 3, so the corresponding covariance matrix must be 3 by 3. So 3 rows, 3 columns. So 3 by 3 matrix. And based on that formula given in that definition, so the element within the matrix C can be calculated by using this. Same as before, I suggest you to divide the calculations into 2 groups. One group for the diagonal elements and the other group for the elements off diagonal. In this question, let's focusing on the off diagonal elements first. So in other words, let's focus on the calculation of the C21, C31, C32, and C12, C23, and C13. But we mentioned the covariance matrix must be symmetric about the diagonal direction. So we do not need to calculate the elements within these 2 triangles. We just focus on 1 triangle. After that, we just map it to the other triangle. That should be much easier. Okay, so in other words, what we need to do is to determine the C12 value, C13 value, and C23 values of this within this triangle. And then after that, the corresponding values will be given to the bottom triangle. Okay, so C12 is the covariance of the x1 and x2. That's equal to, equal to 0. Okay, in the test and exam, don't just give me the answer equal to 0. You must give me the reasoning. But here, I want to save some time, so I give you 0 because I can tell you the reason. Okay, the reason of this is because of the independency of the elements or random variables within the vector. x1 and x2. So between these 2 random variables, we want to evaluate what is the covariance. Can you recall what is covariance? Covariance is the linear relationship measure between the random variables. If the x1 and x2 are independent between each other, they must also be uncorrelated. If they are uncorrelated, that means they do not have a linear relationship at all. If 2 random variables do not have linear relationship, so the covariance must equal to 0. So this is reasoning. Again, in the test and exam, please tell me the reason before writing the 0 value in this calculation. Okay? And then for the C13, C23, actually I don't need to do any special operations. The result are 0 and 0. This is all because of the independency condition given the question. And then for the elements within the bottom triangle, same reason, values are 0, 0, 0. So in the final result, you can see regarding the off-diagonal elements in the matrix, the values are all zeros. Of course, if the independency condition is not given in the question, you have to calculate the covariance between any 2 random variables and put the values into the matrix. So this question is easy. Okay, this example is easy. Now next question, how to calculate the covariance values for the diagonal elements. We have mentioned a special feature regarding the covariance matrix that the value of the elements along the diagonal direction must be the variance of the corresponding random variable. In other words, this C11, C22, C33 should be just the variance of the random variables x1, x2, x3 respectively. So we just need to use condition given in the question. All 3 random variables given in the vector are all unit variance. Then these 3 elements are just 1, 1, 1. Then finish. Okay. So easy example. Okay, let's move on to the next part. Okay, now we come to a special case. So Gaussian distribution. So where's that? We want Gaussian distribution here. Okay, now the random variables within the vector x, the x1, x2, xn transpose, so column vector, are said to be jointly Gaussian if their joint PDF is given by such joint PDF. Okay, the format of this joint PDF is still following the pattern of the Gaussian distribution we introduced before, but the elements within this formula becomes a little bit more complicated because you have in total n random variables within the vector. Again, I will not request you to memorize this formula, but you must understand the notations, the elements within the formula. For example, Cx. Now you know that it's a covariance matrix. The mu x, mean vector. The lower x, the vector of the parameter. Something like that. So you must understand how to use them and how to derive them. Then after putting them into this formula, you derive the joint PDF for this jointly Gaussian distributed random variable vector. Okay. Okay, in addition to this joint PDF, some important properties are associated with this Gaussian distributed random variables. You need to understand all of them very well. First one, the multivariate Gaussian distribution for any order n is fully specified by only the first and second order moments. In other words, if you got a Gaussian distribution random variable, you know its moment and central moment. That's enough. If you got a group of Gaussian distributed random variables, okay, the first moment, the second central moment should be sufficient for you to fully describe the features of them. Okay, the first formula. For other types of the distributions, this is not true. The full feature of the other types of the distribution may need you to use other higher order moments to fully describe the features of that. Okay. Next one, the family of all marginal PDFs of Gaussian distribution are also Gaussian distribution. We have mentioned that in the two random variables cases. Okay, but this is true for n random variable Gaussian distributions as well. Okay. Next one, the family of all conditional PDFs are Gaussian as well. Next one, if the jointly Gaussian random variables are uncorrelated, then they are also independent. So this is one important feature we are going to use in the future study. Please make sure you really know this one. Only for Gaussian type distribution, if they are uncorrelated, then they are independent. So we have said before, so if they do not have linear relationship, then they don't have any relationships. Okay, this is true only for Gaussian distribution. Next one, the linear transformation of a jointly Gaussian random vector is also a jointly Gaussian random vector. This linear transformation means using a linear matrix to convert this vector. So we are going to have a look at this one in the next slide, but I just gave you the information here. Okay, so linear transformation of Gaussian is also Gaussian. Okay, finally, the sum of jointly Gaussian random vectors is also jointly Gaussian. So if you got two vectors of Gaussian distributed random variables, the summation of them is also the another Gaussian distribution. Okay. Okay, this is important properties regarding the Gaussian distributed random variable vectors. Okay. Okay. Another important topic. So the linear transformation of the random variable vector. Now, in this case, we have got one x vector of random variables. This is again a column vector which consists of x1, x2 until xn. So we have n random variables within this x vector. And the linear transformation means we are using a coefficient matrix to multiply this x vector to produce another vector y. In the y vector, there are also n random variables inside. This means we are linearly transform the x vector to the y vector by using the transformation matrix A. Okay, so this is so-called linearly transformation. So regarding this transformation, I want you to just pay attention to the dimensions. Okay, so regarding this x, we said that is n rows by one column. The transformation matrix A is in front of x, right? So its dimension is n by n. So n by n by n by 1. The result is n by 1. So that means the result y matrix or y vector has the same dimension as x. In this part, please do not write y equal to x by a. This is wrong because you will not be able to make the y to be the same dimension as x. You cannot even get the result of y actually, because x is n by 1 matrix, a is n by n matrix, n by 1 by n by n. Multiplication between such two matrix and vector cannot give you the result. Okay, this is not right. Okay. Okay, let's move on. The mean vector or the expectation of y, that remains the same. So mu y equal to the expectation of the y vector. But the y vector equal to a by x. Expectation operation cannot operate the A matrix because in the A matrix, they are all constants. We do not have the random elements within the transformation matrix A. So we can move the A out of this expectation operation. So A is out of that, and then EX. The EX is actually the mean vector of the X vector. Then the mean vector of the Y is equal to the transformation matrix multiple the mean vector of X. Easy stuff. Okay. Next one. How to evaluate the covariance matrix of the Y? CY. CY equals A by CX by A transpose. How did you derive this result? Very simple. Let's try this out. So we want to evaluate CY, right? CY by using the formula we introduced regarding the covariance matrix equal to RY, the coordinate matrix, minus mu Y by mu Y transpose. So by handwriting, I can't use so-called the boldface font, but you need to understand C and R and mu are all matrix and vectors in this case. Okay, and so what's RY? RY is the expectation of Y by Y transpose. This definition of the RY, the coordinate matrix, minus what's mu Y? We just introduced mu Y equal to A by mu X, the transformation matrix by the mean vector of X. And this one multiple the transpose of the A mu X here. And inside of the expectation of the first term, Y this matrix, Y is produced by using the transformation matrix by the X vector. So Y equal to AX. So we just put AX here. Then multiple AX transpose minus A by mu X. So for the second part here, the transpose of the A by mu X. A is matrix, mu X is vector. When you transpose this product, it is converted to mu X transpose by the A transpose. So you can see after transpose for each of these two elements, the position of them are interchanged. Okay, that's equal to the expectation of A by X and do the same thing. So give the transpose to each of A and X and interchange their positions. give you X transpose by A transpose minus A by mu X transpose by A transpose. Now I want you to focus on the A matrix. See, A matrix, A transpose, A transpose. With that, the equation cannot operate anything of the real or constant transformation matrix. So we can move the A and A transpose out of the equation operation. So that gives us A by equation of X transpose by A transpose minus it's really long one. A by mu X transpose A transpose. Again, the focus on the position of A transpose A transpose out of the two terms. So we can just move the A and A transpose out of the two terms, or abstract them out of the two terms. So we will be able to derive A by A transpose inside of brackets, but E X xt minus mu X transpose. What is this? That's the Cx. Then we derive the result. Okay, again, this result is important. You must know this very well. And regarding this mathematical induction, first of all, it's not hard. Secondly, if you can go through this one, I think that is a good practice for you to understand some important techniques used in the matrix calculation, cross matrix calculation, the cross matrix calculation. So please go through them. But in this unit, I don't really want you to really memorize this. I want you to know how to do that, not just memory. It's about your skill. Okay. In the test and exam, maybe I will not ask you to just do the exact same question, but I will ask you the similar questions. Okay. Okay. This is the formula. So how to determine the covariance matrix of Y based on the transformation matrix and the covariance matrix of X. Okay. Okay, next one. On top, so we just write the conditions again. So Y equal to AX. So this is repeated component. But next part will be new. So a new concept called coarse covariance. Okay, be careful. This concept is different from the covariance matrix. Covariance matrix is used to calculate the covariance between any two random variables within the same vector. But the coarse covariance matrix is used to calculate covariance between two random variables coming from two different vectors. In this case, one vector comes from X. It's my fault. One random variable comes from X. The other random variable comes from the Y vector. So you can see, regarding this coarse covariance matrix, the notation is CXY. Both X and Y are using the boldface font. That means X is a vector, Y is also a vector. This capital C is used to evaluate the covariance matrix between the elements in the X vector and the elements in the Y vector. That is equal to, okay, coarse correlation matrix Rxy minus the mean vector of X by the transpose of the mean vector of Y. Okay, so this is the definition of it. How to calculate this thing? So the CXY equal to CX by the A transpose. Again, quickly, I will just help you to go through this one. Sorry to say I have to repeat again. Maybe I will not require you to memorize this mathematical induction, but you must understand the steps, the techniques, the skills, the matrix calculation, all this stuff in this mathematical induction, so that you can do it by yourself when the question is changed. Okay, so in this question here, we want to evaluate the course current cxy. We said this is equal to rxy minus mu x by mu y transpose. The rxy is actually equal to expectation of x by the y transpose minus mu x doesn't change, mu y, the mean vector of the y equal to a by x, right? So mu y is the a by the mu x, then transpose. That equal to e expectation of the x by y equal to a by x transpose minus mu x by mu x transpose by a transpose equal to the expectation of x transpose by a transpose. Now I put the a transpose out of the expectation. We have known that, right? Minus mu x transpose a transpose. And then let's just abstract the a transpose out of the two terms. You got expectation of x transpose minus mu x by mu x transpose by a transpose, which give you this term cx by a transpose. Okay, you must know of course the result and some important steps within this mathematical induction as mentioned. Okay, get that here. And everyone please be reminded another important thing. Before this slide, we have said, okay, for the covariance matrix, all the diagonal elements are the variance of the corresponding vulnerable, and of the diagonal directions elements are the covariance between the corresponding vulnerables. This is not true in this case because this is the coarse covariance matrix. So the elements along the diagonal, yes, you can see this C11, C22, C63. These notations are same as the covariance matrix, right? Yes, the notations are similar, but the meanings are different. Because in this evaluation of the coarse covariance matrix, we are involving the two vulnerables coming from two different vectors. So this is C11, for example, or C22, whatever. This diagonal element is indicating the covariance between x1 and y1. This first number 1 in the subscript is the index number of the vulnerable coming from the x vector, so x1. The second one here is indicating the index number of the vulnerable coming from another vector, y vector, so y1. So x1 and y1 are not the same thing. So in other words, so because x1 and y1 are different, so the covariance between x1 and y1 is not the variance of either x1 or y1, something like that. Okay, so even though inside of the coarse covariance matrix, the notations are similar to that of the normal covariance matrix, the meanings are different. Be very careful, please. This is the first point. The second point, maybe I want to ask you, do you think the coarse covariance matrix is a symmetric matrix? In other words, my question is C12 equals C21? Is Cij equal to Cji? Answer is no. The reason is here. For this coarse covariance matrix, the Cij means the covariance between xi and yj, but the Cji equals covariance of xj, yi. They are not the same. So this xi vector, so element, for example, x1, x2, xi, xj, whatever, until xn, for example, this is our x vector. Our y vector is y1, y2, until yi, and yj, until yn, these two vectors, the Cij is calculating or evaluating the linear relationship between this xi random variable and this yj random variable. Do they have linear relationship? That is Cij. The CJI is another story. CJI is evaluating the linear relationship between the xj and yi, so another group of random variables. So if there's no specific conditions regarding this story, so these two groups of random variables may have different relationships. The Cij and Cji in the coarse covariance matrix case are usually not equal. So in other words, the coarse covariance matrix is not generally a symmetric matrix. Okay, so please be very careful between the difference regarding the difference between the coarse covariance matrix and covariance matrix. They are different. Okay. Okay, now some further extension regarding the linear transformation. Okay, a condition remains same. So you have the x vector available, and the y vector is equal to the transformation matrix A multiple this x vector. This whole story, and we know the Cy show as this is covariance matrix of y equals A by the covariance matrix of x by A transpose. So I have done the mathematical induction of this one before. And the new thing in this case is the transformation from an uncorrelated random vector x. That means y is transformed from x by A, but x is an uncorrelated random variable. If the x is a vector of uncorrelated random variables, the covariance matrix of x, or in other words, the Cx must have a special feature. Along the diagonal direction, that should be the covariance. That's my fault. Sorry. So along the diagonal direction, there must be the variance of different, random variables in the x vector. So we call that as x1 square. So this variance of the first element, sigma x2 square until sigma xn square. So variance of different random variables of x. And off diagonal, all the elements must be 0, 0, 0, all zeros, because we said, first of all, so in this x vector, all the elements are uncorrelated, which means no linear relationship between each other. And we are evaluating the covariance matrix of x. So all the off diagonal elements are calculating or evaluating the linear relationship between the corresponding random variables in the same vector x. But they are uncorrelated, no relationship. So the covariance are zeros for all the off diagonal elements. Okay, so that is a special feature. And so of course, using such Cx in this calculation should be very easy. A is a square matrix. A transpose is another square matrix. And in between this A and A transpose, you just have Cx, which is actually a diagonal matrix. You just do very simple calculation after multiplication between elements. You should be able to evaluate the Cy very quick. Okay, so this is easy question. And this question could be much easier if all the random variables within the x, so x equals to x1, x2, until xn, right? So if all the elements, all the random variables within this vector are unit variance, so sigma x1 square equals to sigma x2 square equals sigma n square equals 1. So unit variance. If this is true, so Cx will be converted to 1, 1, 1, 1, 1, and all zeros. And when you use this, we call that as identity matrix, right? In between the A and A transpose. If you have this CY equals A by CX by A transpose. But we said, if this got unit variance uncorrelated vector, then this covariance matrix of the X vector will be an identity matrix. So that will be equal to A by I. I is used to denote the identity matrix, right? By A transpose. This is equal to A by A transpose. Got it? Very simple thing. Okay. Okay, next part. By the way, in this slide, we just discussed the features about the transformation from an uncorrelated random vector. In the next slide, we are going to see the features of the transformation to an uncorrelated random vector y here. So when we discuss this topic, okay, condition remains same. So we have known the vector x is equal to the column vector with x1, x2, until xn. So n random variables inside. The A is the n by n transformation matrix. So all the same. The Y matrix is produced by using A matrix, the transformation matrix of A, multiple the X vector. So the Y vector is n by 1 column vector as well. So Y is transformed from X. Or in other words, we can say we are using the transformation matrix A to transfer the X vector to the vector Y. But in this case, we want the random variables in the final Y vector to be uncorrelated between each other. If the elements or the random variables within the Y vector are uncorrelated between each other, so the covariance matrix of Y, here we are using special notation temporary to denote the covariance matrix of the Y vector, must have the feature like so this can help you to recall what I've learned, right? Because all the elements within the Y vector are uncorrelated. So along the diagonal direction, the sigma y1 square, sigma y2 square, until sigma yn square. So they are all variants of the individual random variables within the Y vector. And for the off-diagonal elements, because they are all uncorrelated, so within this covariance matrix of Y, values are all zeros for these off-diagonal elements. And in this covariance matrix for Y, because we have only non-zero elements along the diagonal direction, so this covariance matrix of Y is called a diagonal matrix. This means the off-diagonal elements are all zeros, okay? And we can just guarantee this covariance matrix is a diagonal matrix if the Y is an uncorrelated random variable vector only. Okay, this is what we have known regarding this case, and in our previous discussion, we have already known this. So we just gather all this useful information together to give you a big picture regarding the topic. A new topic for this discussion is how to determine the matrix A so that we can diagonalize the CX is given here, right? So we didn't say the X random variables are uncorrelated. We didn't say it. They could be correlated. In other words, this CX may not be diagonal matrix, but by multiplying A and A transpose around the CX, we are producing a diagonal matrix as the covariance matrix of the Y vector, right? So our question is how to determine the transformation matrix A to diagonalize the CX to produce such occurrence of the Y vector. So here, the transformation matrix A must equal to inverse P, where P is the eigenvector matrix of the CX. And also here, please notice one important property regarding the diagonalization. So if the CX, or in other words, if a square matrix is symmetric, so its eigenvector matrix inverse is equal to the transpose of the eigenvector matrix. This is another topic, but we need to use that later. But I'm not going to introduce background of this one. You may refer to any mathematical textbooks to find the really relevant mathematical inductions. But this is out of scope of this unit. Okay, the diagonal matrix, the corresponding matrix of the Y consists of the corresponding eigenvalues in its diagonal direction. In other words, after we finish the diagonalization by using the A and A transpose around CX, we will produce the corresponding matrix of the Y vector, right? And in this diagonal matrix, so we have the non-zero values along the diagonal direction, right? So all these elements along the diagonal direction are actually the eigenvalues of the coherence matrix CX. Okay, so this whole thing here. Why do we do that? The things like this. You want to, sorry, my fault. You have got the X. You want to just generate a matrix A so that you can produce Y. And all the random variables within the Y vector are uncorrelated. Now the question is how to determine A. This A is also used in such relationship. So A by CX by A transpose. And in this case, we want to use this relationship to help us to determine the A so that, let me just highlight this one. Okay, we are going to use this equation to solve the transformation matrix A so that A can be used back here to produce Y. But how to determine the A here? So as I mentioned, the process given by this formula is actually calculating or deriving the diagonal matrix from the CX. We have known this has already been the diagonal matrix, and all the elements along the diagonal direction are the eigenvalues of CX. And this A matrix is equal to P inverse. And in the P matrix, we got all the eigenvectors of CX. Or in other words, if you are able to know the CX, and of course we can know that, right? If you are able to know the CX by calculating the eigenvalue and the eigenvalues, of course, and also the eigenvectors, we are able to determine this covariance matrix of the Y vector, and also we can determine the A. Once the A is known, we can put the A back into this formula to really determine the Y vector. Okay, so this is the whole story. And now, next page, let's have a look at how to do that. So matrix diagonalization is a process transforming a general square matrix U to a diagonal matrix V by V equal to P inverse by U by P. Okay, actually this slide and also next slide is introducing some fundamental mathematical knowledge. Not full knowledge, it's just some relevant knowledge points which can help you to solve the question, okay? So V is diagonal matrix, U is general square matrix. The P and P inverse and P are just about the transformation matrix, okay? So U is the n by n square matrix given like that. V is an n by n diagonal matrix V, so which have the non-zero values along the diagonal direction only. Such kind of process is called diagonalization from U to V by using the transformation matrix P here. And at the bottom of the slide, you can see one example. So in the middle of the term on the right-hand side, you can see the orange square indicating the general n by n U matrix or square matrix. And around this U matrix, we put a P inverse and P to multiply with this U. So this way can do the diagonalization. And then after we finish this process, so P inverse by U by P, we are producing the V. And the V must have the non-zero elements along diagonal, and off diagonal elements are all zeros. So this is just the process of the diagonalization. But here, please bear in mind, not all square matrices can be diagonalized. So some of square matrix U cannot be converted to diagonal matrix. But what is condition of the diagonalization? So you must have, for n by n U matrix, you must have n distinct eigenvalues. In other words, okay, in my U matrix, this is 3 by 3 matrix, for example, just like this one. So this is 3 by 3 matrix, n equals 3. So from this U matrix, you must have 3 different eigenvalues. And then you can do the diagonalization. But how about like this one? For example, within this U matrix, I got 3 eigenvalues, and 2 of them are equal to 1, and the other one is equal to 2. In such case, can I do the diagonalization? The answer is no, because there are 2 identical eigenvalues. You didn't got 3 distinct eigenvalues. So condition was not satisfied. So in such case, you will not be able to finish the diagonalization successfully. Okay, so please bear in mind the condition is all the eigenvalues must be different between each other, so distinct eigenvalues regarding the U. And if U can be diagonalized, the diagonal matrix V just have all the eigenvalues of U in the diagonal direction of it. In other words, we go back, okay, to the example. We said in this case, U matrix in the middle is diagonalized by the P matrix to produce V. And after you finish the diagonalization process, in the V matrix here, along the diagonal direction, you got 2, 1, and 3. These 3 values, right? These 3 values are just the eigenvalues of U matrix. And you can see these 3 values are different. 2, 1, 3. So distinct values. Okay, so this case. And keep going. The transformation matrix P is the eigenvector matrix. The column of P are the eigenvectors of U, and the order of these eigenvectors P in P corresponds to the eigenvalues in the V. So what I mean is given here. Now let's see this explanation first. See here, this V is the final result. So diagonal matrix after the diagonalization process, right? And this P is the transformation matrix. So P is used at here, and inverse P is used here. Okay. So in the P must be n by n matrix as well, right? So the P square matrix must have n columns, and each column is 1 eigenvector. This eigenvector is corresponding to the eigenvalue in V at the same or in the same column position. For example, the second column in the transformation matrix P must be the eigenvector corresponding to the second eigenvalue given in the diagonal matrix V. So that, in other words, when you do the diagonalization, the final diagonal matrix and also the transformation matrix P are all related to the eigenvalue and the eigenvector of this square U matrix itself. Okay. Now, example, how to do that. Sorry for the tiny font, but because there are so many things, I think you can zoom in on your side to see the mathematical things clear. Okay. Now, We assume a square matrix U is given like that. And we need to find a transformation matrix P, which can convert U to a diagonal matrix V here. Okay, we have known regarding the matrix V, diagonal matrix V here. Along the diagonal direction, we got the eigenvalues of U. And for this transformation matrix P, each column is one eigenvector of the U matrix. Like that. So in other words, we need to determine the eigenvalues and eigenvectors of U matrix. So this is our first step, so determine the eigenvalues. And how to do that? How to determine the eigenvalues? I think I have already given that. Just give me 1 second, please. Okay, in next slide, I'm going to show you how to determine the eigenvalues. That is another topic. Let's just finish this idea, okay? So we assume we have done the calculation, and then we got 3 pairs of the eigenvalue and eigenvectors. First one, eigenvalue equal to 2, and the corresponding eigenvector is 0, 0, 1. This is a column vector, okay? Second pair, lambda2 equal to 1. This is eigenvalue, and eigenvector is given as P2. So for the third pair, so eigenvalue is 3, and P3 is also given. So now we got these 3 things. Now pause here, check. Are all the eigenvalues distinct between each other? 2, 1, and 3. So okay, because you have 3 distinct eigenvalues for this 3 by 3. So n equal to 3, right? 3 by 3 square matrix U. So we can move forward to finish the diagonalization. Okay. Next one, let's start the diagonalization. V equals P inverse by U by P. So V should be just a diagonal matrix, and the eigenvalues are just along the diagonal direction. So lambda 1, lambda 2, lambda 3. So 2 and 1 and 3 are given here. These 3 values comes from lambda 1, lambda 2, and lambda 3. Okay, and the corresponding transformation matrix P should be an n by n square matrix. N by n means n rows, n columns. In this case, n equals 3, so 3 by 3, right? It must have 3 columns. Each column, for example, column 1 should be the first eigenvector corresponding to the first eigenvalue. In this case, we are getting that eigenvector from here, 0, 0, 1. So this column vector will be given as the first column in the transformation matrix P. And then P2, P3. So the other 2 eigenvectors are given here. After this step, so we can write, okay, I think this is, that's right. Let me see. Guys, sorry, I think the notation I used are a little confused. Let me just ignore this one. So what we are doing is the V equals P inverse by U by P using here. Okay, this is just background mathematical information. But regarding our covariance matrix, so what we are doing here is, remember, here is CX, so covariance matrix of the X vector. And you are going to find A and A transpose so that you can diagonal the CX to the covariance matrix of Y, which is a diagonal element. In this case, the U is the analog of the CX. The inverse of P is corresponding to the A matrix, and P is corresponding to the A transpose. That. Okay, so this is the idea we used. And just one more background information. So how to determine the eigenvalues. Same example. So you got this U matrix. So the values remain same as the previous example. And we want to determine the eigenvalue or eigenvalues lambda for this square U matrix. So we need to use the determinant. Determine the determinant of U minus lambda I. And then U is not changing. U is here. lambda is something you want to determine, and lambda should be a vector so far containing all the possible eigenvalues inside. Okay, and the I is one 3 by 3 identity matrix. So then 1, 1, 1, and all other things are zeros. So by this calculation, inside of this determinant calculation, got this result. And then the determinant of this gave you this. Based on this one, we are calculating the value, but this value is actually a function so far because the lambda has not been known. So we have such a function in terms of lambda. And this whole thing, make the whole thing equal to 0. In other words, please make the determinant of the u minus lambda to 0. Then you can determine lambda. So for this case, lambda equal to 2 or 1 or 3. So easy calculation, right? So once you determine the eigenvalue, how to use the eigenvalue to determine the eigenvector here? Okay, we are going to use the relationship given here. U square matrix multiple one eigenvector is equal to the corresponding eigenvalue multiple the same eigenvector. So let's see the example here. So we are using this relationship and then using the U matrix multiple this so-called unknown eigenvector equal to the corresponding eigenvalue multiple the same eigenvector. Now we can substitute one lambda value into this one. For example, if the lambda 1 is equal to 2, so you can put the number 2 to this lambda 1 equal to 2. And then after this step, just use the matrix calculation to convert this matrix formula into a number of equations in terms of the pi1, pi2, pi3, and then solve these three unknowns. After you solve these three values, put them back into the column vector to finish the calculation of the first eigenvector. This eigenvector is corresponding to the eigenvalue you used. Okay. Again, this is not new to you, but you may have already forgotten it because this should be maybe year 1 or year 2 math units contents. So I hope this can help you to recall these details. If you want to know more details, please refer to your mathematical textbooks. There's one more thing we need to notice. Final result. Please note, after you solve the eigenvector like this, in most of cases, the magnitude of such vector is not unit. So you have to do one more step to normalize this vector. How to normalize? You just divide this vector by this square root, the summation of the square of each element within this vector. This is used to do the normalization to make the size of this vector to be unit. Okay. And then this is just the procedure. Final result are given here, here, and here. So all the vectors given in the final result have already been normalized. Okay, and then you got 3 pairs of them. After you got 3 pairs of the eigenvalue and the corresponding eigenvectors, you can go back to the questions and give the result here, and then move on to the next step. Okay, so this is about the diagonalization of a matrix. This process, the diagonalization, should not belong to this unit. That should be part of the preliminary knowledge. But because we are going to use this knowledge to process the, the vector, the random variable vector transformation, so this part of knowledge will be essential. Okay, make sure you understand how to do that. A quick summary on the transformation to an uncorrelated random variable. So you have been given the condition of a random variable vector x, and you are going to find, first of all, a transformation matrix A, which converts x to an uncorrelated random variable y, based on y to ax. So A is the one you need to find out. Based on A and X, you can determine Y, okay? And then you must be able to determine the uncorded real number Y, okay? So how to determine A? So determine the coherence matrix Cx of the vector X first. Step 2, calculate the eigenvalues and the corresponding eigenvector of the Cx. If the Cx doesn't have undistinct eigenvalues, then Cx cannot be distincted. It cannot be diagonalized, and A cannot be determined. So no solution. Okay. And then if you have the undistinct eigenvalues, you can move on. Next one, completing the diagonal matrix of the Y and the eigenvector matrix P. We need to check this one. Okay. Therefore, because you have already known the P, so the transformation matrix A is equal to P inverse, which is also equal to P transpose, because the Cx is a symmetric matrix. Okay. Finally, we can use the determined A from step 4 to calculate the Y vector from the A and X. Then finish. Okay. And the next one, I think we don't have too much left in this lecture. Independently and identical distribution. Normally, we call such kind of thing as IID. So IID again here. So independent and identical distribution. So this is used to describe the relationship between two or more random variables. For example, if I got X, I got Y, I say X and Y are IID, so independent and identical distribution. So this so-called IID has two meanings. First one, independent. This means the two, of course, maybe more, okay? The random variables are independent between each other. Of course, they are uncorrelated because they are independent, okay? This is first meaning. Secondly, the distribution of these multiple random variables are identical. So what do you mean the identical distribution? Okay, that means the type of the distribution are the same between these random variables. For example, they are all Gaussian distribution, they are all exponential distribution, so the type of them are the same. Okay, and also it means all the important features like the mean value, the variance are the same regarding these distributions. In other words, this so-called identical distribution between the multiple random variable means they have the same type of distribution, and the mean value, the variance of all these random variables are the same. Okay, so independent and identical distribution. Okay, and the next one, central limit theorem. For this case here, first of all, we have a collection of random variables denoted by the x1, x2, x3, until xn. Okay, they are all IID distributed random variables. That means x1, x2, x3, until xn. These n random variables are independent between each other, and they have all the same distribution type and features. Okay, and then we are going to use this n random variables to construct a new random variable. We call that as Sn. So in other words, we are adding up all these n IID, so independent and identical distributed random variables x1 to xn together to produce Sn. Okay. Now, regarding this Sn here, regarding this new random variable Sn, its mean value, Sn is new random variable, and its mean of Sn is n by mu x, in which the mu x is the mean value for each individual x random variable. The variance of the Sn is n by the variance of each single x random variable. And if the number of the IID random variables are big enough, very large, approaching to infinity, then we can say the new random variable Sn must be following a normal, of course you can call that as Gaussian, normal distribution. And the mean value of the Sn will be at n mu x, and the variance is n by sigma x squared. Okay, this is a very simple thing. I repeat again. You have a collection of IID random variables, x1 up to xn. In total, you have n random variables in this collection, and we are adding these n random variables together to produce the Sn random variable. If the n number of the x random variables, the IID random variables, are big enough, so this new produced Sn random variable must follow normal distribution, and the mean value of this Sn new random variable is at n by mu x, and its variance is n by sigma x squared. Get that? And there's one more thing we can do. So you have got the Sn, right? So you know if n is large enough, this Sn is following the normal distribution. That's okay. The next step we can do is to do the normalization. This normalization means I want to convert the mean of the Sn to 0. I want to convert the variance of the Sn to 1. So in other words, I want to convert the Sn to another random variable, Zn, and Zn is following the normal distribution, but with 0 as the mean value and 1 as the variance. So in other words, the Zn will be following 0 mean and unit variance normal distribution. But how this Zn is produced? Zn is produced here. So Zn is just equal to. So now here is the normalization process. We are using this Sn random variable minus the mean value of the Sn divided by the standard deviation of the Sn. So that result has been given here. After you finish this normalization, so Zn must satisfy this condition. Zn must be following this distribution. And based on this one, we will be able to derive for that CDF. The CDF of the Zn. You can find this part of formula is identical to that CDF of the single normal distributed random variable, and must be able to satisfy this condition. Or that this is the PDF of Zn. So this is satisfying a 0 mean unit variance normal distribution PDF. Let me just go back to our week 1 contents to check that. Okay, so but the only difference is on the left hand side of these two equations we have such condition. So in other words, so if you want this formula to be true, the number of the IID random variables x must be large enough. Okay, so this is just about the central limit theorem. Okay, a small application of the central limit theorem. So actually here we are going to talk about two different distributions. One is the binomial distributed random variable, and the other one is the Gaussian approximation. So at the bottom in this equation here, you can see we have two parts. This part is the PMF of binomial distributed random variable. So we have learned that from our week 1, right? So you know this one. So when the n is large enough, so what's n? N is the number of the Bernoulli experiments you run in this binomial random variable. Okay, so if n is large enough, if you play the tossing cone game many times in one single binomial trio experiment, and we can approximate this thing to a Gaussian distribution. The reason is, in one single binomial experiment, you are going to play the Bernoulli experiment n times. If the n is large enough, the final result of this binomial experiment is actually the summation of n times IID random variable x. So why is IID? Because between any two times you toss the coin, there's no relationship at all. And also for each single time you toss the coin is one Bernoulli experiment with the same mean and with the same variance, right? So this is the IID random variables within one single binomial experiment. So by adding up all these IID Bernoulli experiments together, result together, so we are producing the binomial random variable here. But this is actually the summation of n times IID random variables. And if the n is large enough, when n is approaching to infinity, so this can satisfy the condition of the central limit theorem. And then the result can be summarized or approximated as the normal distribution. Now, this is our normal distribution. Okay, this means when the number n is large enough in the binomial random variable, so the result can be approximated by Gaussian distribution. Okay, everyone, thank you for attending this class. This is everything for this week. So see you in the practice class this week. Bye for now.